Okay, Assalamualaikum and good morning. So today we would like to discuss tutorial for chapter 1. It is focused on a very wide question about fluid properties. Okay, some of them is mentioned in the class because I would like to, the previous class is actually to revise you about the Navier-Stokes equation, about how derivation of basic flow, and then how we combine a few basic flow to get a little bit complicated flow like a flow around rotating cylinder. Okay, you may have this question from the textbooks, and I also upload this question uh, in my website. Okay, but I don't upload the answer of this one. Okay, you need to print screen and make your own notes, or at least you need to watch this video again to make your notes. So I will upload this video later on in my YouTube channel. So question 1.1. So let's say we have a sphere 1.4 here. So 1.4 centimeter in diameter, placed in a free stream, 18 meters per second at 20 degrees Celsius and 1 atm. So, and then we need to compute the diameter of Renault number of the sphere if the fluid is air, water, and hydrogen. So, for example, this is the question to calculate the Renault number. So, I hope you know you could remember the equation of Renault number, but the most important things that you need to know here is the exact equation or the correct equation to calculate some things. Because, for example, the most common equation in fluid mechanics is actually Renault number here. Okay, but it's not fixed as rho VD. Sometimes we will use rho VL over mu, and sometimes might be we will use rho V hydraulic radius over mu, and sometimes we are okay. So this is the common one because we have three major situation. Okay, so because we have a sphere here, so we get the diameter here. Okay, but actually, so we have a sphere here, and this sphere is located at the flow like this. Okay, so actually the diameter here is reflecting the distance of the fluid travel from the starting point to the end point actually. But with the sphere, the diameter is constant at any direction. Okay, so but in some textbook they were told that the diameter here is reflect the resistant area or the cross-sectional area of this object. Okay, but I would like to say that the diameter here is actually the length of the travel molecule here. Okay, because the limit of this one is actually from we assume that when the Renault number is greater than 5 times 10 by the power of 5, so we assume that the flow is completely turbulent. Okay, so we have this equation, so we substitute all the values, so you will get the Renault number for that sphere if flowing in air, water, and hydrogen. So, and then another thing is, I hope you could remember the common parameter for the common fluid, for example, an air here and also water. So we have the density is almost 1000 kilogram per meter cube. So it is okay for you to use 998 or 1000, because in master level, so we assume that you are start to do your master project, which is a quite specific work. So you need to base your calculation on the temperature. So if the water is around 20 degrees Celsius, so you need to get the correct density for that fluid for in specific temperature. Okay, so so we could calculate the Renault number for in air. So we could calculate the Renault number in air, water, and hydrogen. So here, so the limit is 5 times 10 by the power of 5, because we assume that it is about the fluid, an object here surrounded with liquid. Okay, because if you take Renault number, limit with 4,000, if it's greater than 4,000, and you start to assume it is turbulent when it's greater than 4,000, it is actually for flow in pipe. So means you need to have a pipe here, and then you calculate the diameter of the inner pipe here to get the Renault number. But the nature of the flow is totally different in this question. So this is about the something like this. Okay. So, and then I would like to mention here, okay, this question, it looks simple, but the idea that you need to get from this question is when you are dealing with gas. So gas, okay, we have an example here, hydrogen and air. Okay, please bear in mind that air here, so it's actually reflect the atmosphere air. So mean it is the combination of few gases. So we have hydrogen, we have argon gas, so we have nitrogen, we have oxygen. So oxygen only consists of 20%, might be 21, 22% of the total percentage of air. So when we write an air, so it's reflect to the what we inhale every day. So it is just the combination of gas. So if it's give you the hydrogen here, so it means it is 100% hydrogen gas. So you need to find the density of hydrogen and also the kinematic viscosity of hydrogen. So, and then another thing that you should to take note here is, okay, gas is
Excuse me,
quite,
doctor.
yes,
The previous slide, please.
okay.
What do you mean, rho v r h over mu?
Okay, so as I said, so the most common parameter in fluid is actually the Renault number. So, but Renault in this
I know.
question, okay. So, I would like you to really know the correct equation for certain dimensionless parameter. So, for example, Renault number here, in this situation, you will use rho VD over mu. But
Yes.
sometimes in other application, you need to use rho VL
V
over
r.
mu, and
Yes.
also rho V hydraulic radius over mu. So it's depend on the situation, and the limit of Renault number is changed depend on the situation.
This value from tables?
No. So the L here is the length. So for
No,
example,
no,
if
no,
you,
doctor.
okay,
The RH.
RH. So RH is hydraulic radius. You need to,
Hydraulic
okay, you need to calculate the
radius.
hydraulic radius. Okay, so
Oh,
the equation is cross sectional of your conduit divided by the weighted parameter. So it is used in application called open channel.
okay, doctor. Noted.
Okay. Okay, so
Doctor, may I have a question, please?
yes.
Assalamu alaikum.
Waalaikumsalam warahmatullah.
Doctor, I just wanted to ask you about why didn't we use the general law? It's called PV equal MRT, because we have the temperature here, and we have the mass and volume and pressure. This is
Okay.
my first question. Second, is the pressure here is P gauge or the general or P absolute? Because we know that a P absolute is equal to P gauge plus P atmosphere.
Okay.
Uh, Basically, I have this question for now because I have read these questions and I saw the solutions. That's why I was confused. Why we didn't use PV equal MRT?
Okay, because the question is they ask you to calculate the Renault number. So you the Renault number, the equation for the Renault number is this one. So PV equal MRT and so on and so forth is actually the equation to calculate the properties of that gas. So I will talk this later because that's why okay, in this situation, so we have an air here, a gas, and also the hydrogen here as a gas. So I would like to say here, so for liquid, for example, water, it is incompressible. It is easy, not easy to compress. That's why we don't have any problems to calculate liquid. So when so this is your first answer. First, the answer for your first question is because we need to calculate the Renault number. So the
To be
equation of
honest,
the Renault number is this one.
sometimes when the temperature is mentioned in the questions,
Yes.
most of the students go directly to PVMRT because this law we have it from the bachelor, and that's why we are familiar to use it. That's why I think the
Okay.
majority of the student will go directly to this question to this law. But when I tried to use this law, it was a different solution.
Okay. So if you have PV equal MRT, so if you substitute everything that you have in this equation, so what is your Renault number?
It will be as a result from the M and P, the information listed.
Okay.
Uh, you want me to? Yeah, actually, I dropped the paper.
That actually the idea is in masters, okay, in so the temperature is everything. Even in our undergraduate level in UTM, we will give student all the parameter. We will say, okay, this application is occur at what degree Celsius, at what temperature, at what everything and so on. But not all the information will be substituted in the equation because okay, as an engineer you should to know the real situation, so what is the properties around that one and so on and so forth. That's why we give the temperature, the atmospheric and so on. So one atmospheric here is quite this is common, that is the atmospheric pressure, and 20 degrees Celsius, okay, it's quite near to the common uh, room temperature. Might be so 20, 25, it's 30, it's quite so might be it's slightly different in terms of density of certain gas, the pressure of certain gas, but the changes is not too much, and we could take each we could use. Okay, so that's the idea. And then okay, the first question is because we are now to calculate the Renault number. So by using this one, we cannot get the Renault number because this is not the equation for the Renault number.
Wrong number. Yes, wrong.
Okay, so because the question asks us to calculate the Renault number, so we should mention the equation for the Renault number. Okay, and when we need to use PV, MRT, and so on and so forth. So for example, if you want to calculate very specific, for example, we have an air here, and from the textbook, the density of air is 1.2 kilogram per meter cube is for example, at 0 degrees Celsius. Then you need to calculate by using this gas ideal law, okay, to calculate what is the density at 20 degrees Celsius, because in the textbook might be in the table they give you the density for air at 0 degrees Celsius. So means that 0 degrees Celsius cannot be substituted in this equation because in this situation we are using 20 degrees Celsius. That where you need to use the PV, MRT and so on, another equation. Can you get it?
So in this case, when
Uh,
you mentioned the temperature and the question, that's mean you directed me to go to the tables and choose the row from there for this certain temperature, right?
yes.
Mhm.
Okay.
Okay,
But
okay.
sometimes you can make assumption. For example, okay, so we don't have properties for 20 degrees Celsius at what ATM, but I think it's still correct if you use the property of air at 25 degrees Celsius, for example, because you know the changes of 5 degrees Celsius is not so critical.
You mean interpolation?
So that's the common one.
It will be long.
20 degrees Celsius of air and 25 degrees Celsius of air is not much different in terms of properties. If you want to get a very specific answer, yes, you need to do that.
Yeah.
Okay, that's why in my second, because you asked too fast.
Yeah.
Okay, in next answer, I will show you how to interpolate the value here.
Many thanks.
Okay, because you asked too fast. Okay, you asked too
Thank you.
early. Okay. Okay, that's the idea. Okay, I hope you should understand that in science, it is okay for us to make assumption. So we, for example, in this situation, okay, we are dealing with a 20 degrees Celsius, 180 m here. So and then we have a gas. So we have air here, and then we have hydrogen, and then we have a liquid here, which is water. So the water is not so critical because it is incompressible. So the properties a little bit changes when you use the common table, because sometimes in common table they will take around 25 degrees Celsius or room temperature and so on and so forth. Okay, that's why the density of water here, even though it is incompressible, so in this might be in 20 degrees Celsius, so you'll use 998 kilogram per meter cube, but the Renault number that you get is not so much different if you use the common density of water, which is 1000 kilogram per meter cube. So that's why I think it is not critical for you just to get the properties of what we listed here, okay, air and hydrogen, by taking the common value from the table. Okay, but okay, so this is the answer. And then next, because we are dealing with a gas, okay, we have an air, we have a hydrogen. So air is quite sensitive with a temperature. So the density, the pressure, and so on will change, okay, even though with a slightly increment of temperature. So that's why, as you said, we need to calculate the PV, MRT, and so on and so forth. So, but the idea of PV MRT is actually to find the properties of that gas, not the Renault number. So the Renault number is you need to stick with the equation. Okay, so for example, for the hydrogen here, so it has molecular weight of 2.016. Okay, so it is okay for you if you to make an assumption that the molecular weight of hydrogen is 2, because in common chemical table, so the molecular weight of hydrogen is 2. But to be specific, it is 2.016. So if you need to calculate the by using the ideal gas law, so you need to determine the value of R here. So it is by dividing the 8,313. So this is the constant gas value. Divide by each molecular weight m. So you will get it is around 4,123.5. So and then using the idea of PV and RT. So we use the rho here. Okay. So as you know, as mass over volume will create density. So we have rho is equal PRT. So the P here is 180 m. So and then you have R, and then you have the temperature in Kelvin. So you get the density here. So this is the common way to calculate the density. And then this is to interpolate or to get the more specific answer by the dynamic viscosity, because now to calculate the Renault number, so we have to rho Vd over mu. Okay, and in this stage, okay, we are get the specific value of the rho. So and then now we need to get the specific value of the mu. So from our textbook, so this is the common way to define or to get the value of dynamic viscosity from the reference value. So mu naught here is the reference value and T naught is the reference value. So for hydrogen, so it is given that N is 0.68. So the temperature is 273 Kelvin. So and then the reference value of dynamic viscosity is this one. And then we could calculate, okay, this is the table from the books. So, and then we could get the value of the 20 degrees Celsius, 1 atm of hydrogen. So now this is the Renault number equation. So we substitute the very specific value that we get. So this is density and also this is the dynamic viscosity. So finally you will get 2,393 of Renault number. So Renault number is dimensionless, so it don't have any units. So we have 2393, and if you use the common value, so it's 3, we have 2333. So it's slightly different, but if you common with the Renault number, so the Renault number is actually, if you plot in a graph, so you will plot it in term of log unit. So it's real base just 10 by the power of 0, 10 by the power of 1, and so on and so forth. So that just a different of these numbers might be not affect your calculation. So, but if you want to calculate, it's very specific. So please use this method, because the idea in this question is to alert you that normally gas, okay, all gases is very sensitive with temperature. So it's the properties will change when you change the temperature or the when you change the temperature, the density, the viscosity, and also the pressure will change. Okay, that's it, the main idea in this question. Okay, so the question for 1.2 here is actually just to so this is the question for the textbooks, but what I want to say here is please make sure that you know there is a lot of dimensionless numbers, dimensionless parameter. It is not limited to Renault number. For example, in this question, I think I already give you in my website notes about the dimensionless parameter. So you need to suit your application with the dimensionless parameter. So normally it's the Renault number, because Renault number is the most the usage of Renault number is to determine whether it is laminar or turbulent. So, but not all application will stick with a Renault number. Okay, for example, in open channel, we are more with a Froude number. So, and then when you go about temperature a little bit, so you have a Nusselt number, you have Prandtl number. Okay, in this situation, if when you have a wire here, and the wire is start to vibrate up and down and give some certain frequency and so on and so forth. So the dimensionless number that suit with this oscillating mechanism is the Strohal numbers. Okay, so the idea, so this question will answer the Strohal number, but what I want you to know is please make sure that if you want to solve certain problems, so please make sure that you are using correct dimensionless number.
Excuse me, doctor.
Yes.
Can you please give us some tips about the numbers, Froude and Renault, and when exactly we can use it?
I think I already upload notes in my website. You just download all of them, and then you find about the dimensionless parameter, or you just search in Google. You search the dimensionless parameter, and they will tell you.
Okay.
Okay.
Excuse me, doctor.
Yes.
What about all the equation? Because based on after you present this tutorial question, I found that my problem is I don't know which equation to apply, because too many of it. Do you think we can have a list of like the mathematic type of list of equation then we can refer to it. Then it's faster and easier for us when we solve the problems.
Okay, so okay, we first let me finish the chapter 1 tutorial first, and
Okay.
then actually in our syllabus for chapter 1, 2, and 3, our major concern is uh the idea of Navier-Stokes equation and the way you solve problem using the Navier-Stokes equation. So I will tell you, okay, this is the equation that you really need to understand and remember. Okay, so
Okay.
this is just to give you ideas from the beginning, the properties of fluid and so on. But this is actually, it is good for you to remember this one, to know this equation and so on. But our major concern is Navier-Stokes and its application.
Okay.
Okay. Okay, if you want to start to remember now, okay, I think I already give you notes about the continuity equation. We have du over dy plus dv over dx equals 0, and then we have Navier-Stokes equation of x axis, y axis, z axis. Okay, you just remember that one first. Okay,
Okay.
okay. So this is just the beginning of the textbook. Okay, we go slowly. Okay, so this is just another example. Okay, not we I don't. So it is okay for you not to remember this one, but what you need to understand is not all the application will use Renault number, because sometimes in when I listen we have presentation of master project, or even in master viva, master by research oral examination. So student will always calculate Renault number even it is not necessary. Okay, so Renault number is not all the not necessary for all conditions. So and then this is if you read the textbook, so we have the equation of Strohal number here. So the question asks us to calculate what is the velocity, which give it is 0.2. So the 0.2 here, if you read from the textbook, is actually the standard value of Strohal number that at least that's permissible to occur in a wire string. Okay, so and then it is around means that the velocity of air, it is around 10.24 meter per second. So mean if the flow is more than 10.24 meter per second, so the wire will vibrate roughly. Okay, so and then we could calculate the Renault number here. So and then we found that it is 5,461. So okay. So
Doctor, excuse me.
yes,
In this question,
okay,
why we went to the Renault number? We find the Stroud number and velocity.
yes,
Does the question ask us to find the Renault number?
no.
So
So
why we have to?
okay, normally, okay, normally, if you start to do your master project, or you start to make some research in fluid mechanics and so on and so forth. So in fluid mechanics, we are not. It is not common to represent the velocity in terms of linear velocity, which is in 5 meters per second and so on and so forth. Because, okay, for example, you have a wire here, okay, and then you have a diameter here, and then you have the velocity here. Let's say this is 5 meters per second, and the diameter here might be 5 centimeters. Okay, normally in research of fluid mechanics, we will convert the velocity into the Reynolds number. Because if you stick with this 5 meters per second, yes, you could draw a graph which is in x-axis is velocity, which is you have 0, you have 1, 2, 3, 4, 5, 6, and so on and so forth. But your graph here is only specific for 5 centimeters condition with certain velocity. So it cannot be compared with other application, and it is not easy for you to validate your result. That's why in fluid mechanics research, we will convert all the velocity in terms of Renault number, because it will give you a dimensionless parameter which is suit with so many applications. Because
You mean it is general? We make it general.
yes, we
Uh,
generalize the parameter, because
so
in
in every question we have to find the Renault number after we find Strohard or Weber or another numbers, right?
no. So this is just I just calculate the Renault number, because
Okay.
okay, because so if this question, okay, ask, okay, if you answer with the final Strohard number of this one, okay, it is correct. No need to calculate the Renault number. Okay, so the idea is that I want let you know is in fluid mechanics commonly we are using Renault number to show the velocity, because it normalize, it eliminate the idea of a diameter of 5 centimeter and so on. So they will give you in general terms, because in Renault number here you have diameter, density, mu, and so on and so forth. So it will generalize the diameter, which is 5 centimeter here, the velocity as a Renault number. Means now it's easier for you to compare with other results. That's why if you start downloading journals about fluid mechanics, they will give Renault number versus another parameter. So I just want to say like that one actually. Okay. Okay, it is not necessary for you. Okay, and then this is another calculation. Okay, so this question is just found is from the textbook. So the idea is if you have something, because we are dealing, a lot of our problem is about dealing one object here that flow inside a fluid like this. So it can be in two situations. One is might be the object here is static and the flow is flowing, the fluid here is flowing with certain velocity. Or we have in the reverse condition, so the object here is moving at certain velocity, and this object is moving inside a fluid which is static in the first place. Okay. Okay, but according to the idea of relative velocity, so you could change this situation into this one. So that's why when we want to do research about car, the moving car, so what we do is we make the model of the car is static, but we flow the wind at certain velocity. That will reflect the situation where the car is moving at certain velocity while the air is actually static. Okay, that's why in a lot of fluid mechanics journal, if you read it, so the evaluation, the experimental or the simulation will conduct the object is static and the fluid will flow at certain velocity. Okay, and then when if this occur, so another parameter will go is, so for sure you have velocity here. So and then the velocity will create pressure. This is already known because we have Bernoulli pressure for the incompressible flow. So when you have velocity, so it will create pressure. So and then if this pressure acts at certain area, so now it's will create force, because you know force is equal of P times A. So now another parameter that comes out from the fluid is actually the force. So in moving fluid, okay, the common force that you need to know is actually the drag force and also the lift force. So this is the common force that comes out when you have a fluid flow at certain speed. Okay, so and then the flow here, Okay, so for example, in this one, we need to calculate the drag force here, and sometimes the drag force will show in terms of coefficient. So we have a CD here. So I think you already know that the drag force FD is a CD time 1/2 rho AV square. So this is the common idea of the drag force. So as I said here, so and then for example, in this question, so you have U is equal 12 meter per second. So if we calculate the Renault number, so you will get 6,400. And then we could get the value of CD here by using the chart here. So for example, we have the 6,400 velocity, 6,000, it is 1,000 might be around here. So might be we have 1.1.
After how you get the diameter?
Oh, okay. So this is might be the assumption. We don't have any diameter here. Okay, let's say the sphere is 0.008 meter. Okay, is that okay? Because what I would like to say here is actually the combinations, the idea of first when you get the velocity, so and then the velocity will have the pressure, and we talk about the pressure, and then with the pressure act on certain area here, so will it create force. So and normally for situation of we have the object surrounded by fluid here, so it will create two type of force, which is drag force and lift force. Okay, please assume that the diameter of this okay, let's say assume that the diameter of the sphere is 8 millimeters. Is that okay?
Doctor, please. The
Yes.
value of diameter from the previous problem.
Really?
1.12.
Okay, I'm sorry.
Yes.
Okay.
The previous one.
Okay, I'm sorry. So okay, so let's say it is come from the problem 1.2. So the diameter is 0.008. So we substitute, and the Renault number is 6,400. So we get we could estimate the value of CD by looking at the graph here, and then we could calculate the drag force by using this equation. It is 0.76 Newton per meter per unit meter. Okay. So what I want to say here is actually I wanted to show to you here, as I said previously, normally in fluid mechanics research, we will use Renault number to reflect the velocity. It is, yes, we have 12 meter per second here. So might be you could have a graph with a speed here. So we have the 1, 2, 3, let's say this is 10, 11, 12, and so on and so forth. So as I said previously, why we always calculate the Renault number, because the Renault number will be normalized another parameter. So it's quite useful for another researcher, and it is quite easier. It's easy for you later on to compare your result with another result.
Doctor, excuse
Yes.
me. Every time when we have when the question asks us to find the drag,
Pardon me,
we
I
go
cannot hear
direct
you.
to this table.
What? Please repeat your question.
Every time when the question asks about the drag force, we
Yeah.
go directly to this table, right?
Yes.
Thank you.
Okay.
To calculate the drag coefficient.
Okay. So actually this table is used to get the value of CD. Okay, you will take the value of CD and substitute with this common equation. So this is the common equation to calculate the drag force. Okay, but be careful. Okay, this is might be the drag coefficient for a circular cylinder. So means this is only valid for a circular cylinder like this. Okay, for any kind of diameter, and for any a wide range of velocity. Okay, that's why we use Renault number. because we want to eliminate the effect of diameter and the velocity. If not, for example, we are not using Renault number, so we are using speed, for example, 1 to 3 in meter per second. Okay, and then this chart is actually valid for a circular cylinder with certain diameter. So might be this is only for the 0.008 millimeter and meter, because you need to be specific for its diameter, because you give the specific value of speed here. That's again, I would like to say here that Renault number is might be the most important things, because we try to normalize the velocity. But okay, please do not please also take note that another parameter, dimensionless parameter, is must be used in certain application. Okay, so this is this one, and normally force here is in Newton, but in fluid mechanics sometimes they will give you in term of Newton per meter, because we always calculate in two-dimensional. For example, we have a circular here. Okay, so actually if you read about this one, so the value of A here is actually the resistance, the projection area. Okay, the idea here is the projection area. Okay, so if you have a circular here, okay, you just imagine that you have a torchlight here. If you do like this, so you will get a reflection of its shadow. So this is the projection area. So the projection area, the area is the height of this one, means the diameter of the cylinder times the length of the cylinder. So however, to make this calculation is useful for so many people, so we take the length here as 1 unit. So we take it as 1 unit. Okay, means that we divide the answer with its own width. Okay, with its own width. That's why the answer here is Newton per meter. So it means that the drag force here is 0.76 Newton per unit meter. So it means that if you have cylinder which is 3.5 meter long, so you just multiply 0.76 times 3.5 to get the total drag force that occur on that cylinder. Okay, that's why sometimes in when you read journal, so they will always divide their own answer with the width of that object. Okay. So and then so this is the idea. Okay, we will learn about this in chapter 2 and chapter 3, how to develop this equation. But I want you to know here is, so this is the calculation. Okay, please take note that in fluid mechanics, the idea of no slip condition is actually the one of the important condition that you need to understand. So the yes.
If we going to compute the lift force,
Yes.
so that coefficient we just find from the coefficient table for the lift force, right?
Yes.
It's same
Yes.
same idea, right?
Yes. So the lift force is also you need to change into the lift force here. So it is equal CL.
Okay, understand. Thanks.
Okay. Okay. Okay, so in question 1.4 here, it is please make some revision about the idea of no slip condition. So the no slip condition means that the molecule here will stick very hard on the surface. So as a result, the velocity of this molecule will stop at all. So the velocity, okay, the velocity will equal to 0. Then the molecule, the velocity here, okay, the velocity distribution can be drawn like this. Okay. Good. So this is the common idea of the no slip condition. And then, so but what you need to do, what you need to understand here, so we have two type of situation. One is flow in pipe, which is used in this show in this diagram, and another one is the flow around bluff body. Okay, so we go for the flow in pipe first. So that's normally in flow in pipe we will calculate, or we will assume, we make calculation when the flow is steady. So mean all the flow is in developed flow, in fully developed flow. Why? Because at the entrance length here, okay, the velocity, okay, let's say we have a free stream velocity here. So because it's not contact with surface, so we assume that the velocity is in rectangular shape like this. So means the distribution will be equal along uh, at all the points. Okay, when it's enter the pipe, okay, so it start, yeah, the molecule here will stick very hard, so it stop here at the wall, and then only the molecule that the second molecule that will flow. However, because it stick with the not moving molecule, okay, you could so this is the wall. So we have a molecule here which is 100% stop. Okay, the velocity is 0 now. Okay, and then the second molecule here will still feel the resistance here. So, and then this resistance is not so strong. So that's why the molecule here will move at certain velocity. But because it's touch, connect each other, so the velocity of this molecule is actually very slow. That's why we assume that the velocity distribution in the entrance length here will become like this. So it start to develop the velocity and so on and so forth. So this is why we have another second curve here, because it just to show us the development of laminar and turbulent boundary layers. So we learn about boundary layers later on in chapter 4, 5, and 6. Okay, but why boundary layers occur? It is because we have a no slip condition that will create, that will give us a different velocity distribution. So, and because the flow is in a pipe, so means that it has limitation in terms of, so the cross section area, the diameter here is fixed. So later on this velocity will meet each other at the center point, because this is the most less friction in the pipe. So then after it's reached its develop condition here, so we could assume that, okay, this is the it start this phase which is the fully developed flow. So means now here the velocity distribution will occur like this. Okay, so if you want to draw the velocity distribution, so it is okay for you to draw something like this. So it is okay, because we assume that this is the no slip condition. The velocity is 0, then the velocity will occur and the maximum velocity occur at the center point. Okay, however, for this one, it occur when your diameter of pipe is large. So means that we have a velocity, this no slip condition here. The velocity is 0, and then it starts the next molecules velocity is will come a little bit faster, and so on. After a certain distance, so it will reach its steady state condition. So it means the velocity is not increase anymore, and then it start to flow at the same velocity. That's why it's draw like this. Okay, so means that the distribution, okay, until the gradient of velocity until this level, and at this level, so the velocity will become constant. Okay, so this is the idea. And then what is the here is, so here is the velocity equation for the velocity distribution. So we have the velocity distribution here. Okay, so we just assume that, for example, okay, we enlarge this one, So and then let's say we have this one, okay. So and then it start a straight line here because the velocity is become constant from this stage. So this equation is actually to reflect the curve of this velocity distribution. Okay, let's say we have a molecule here. So the velocity is equal to 0. And then we have another molecule here. Okay, and then this molecule will flow with certain velocity. And this velocity will represent with the small u. So this is the common terms of velocity distribution. And then when it reach the average velocity here, okay, which is the constant velocity here, we will show this velocity as capital U. So as shown here. So in this graph, they will give you the U naught. Okay, so means that it is equal to the U naught here. But sometimes in another textbook, they will use a capital U. So just in my handwriting, okay, this is not a common symbol. So just for my handwriting, I will write U with a bar like this to differentiate between the small u and the capital U. Okay, so in this question, so it's just to calculate, okay, but in chapter 2 and chapter 3, we are going to derive this velocity. Okay, let's say we have the r is constant, so we have the u max is 30 meter per second, the r is, everything is here. So this is the experimental show in your textbook, how the velocity distribution occur in a laminar flow. So because the Renault number is 1600. Okay, so first, because in this equation, okay, the velocity, the c here is the constant, so we need to calculate what is the constant here. So because this equation is something like an equation of a line. Okay, so I think you already know that we have x and y here. So actually it is a line equation for this curve. So what you need to do, how to get the value of constant here is by substitute any coordinates on this line. Okay, however, it's not called the coordinates, it will call as a boundary condition. So later on, we have a question that have boundary condition and so on and so forth. So the idea of boundary condition is actually we represent a coordinate that occur on this line. Okay, so in this situation, they will give you that u max is occur at r0. So it shows that. So this is a radius because we are talking about flow inside the pipe. So this is the radius, and as I said, the maximum is occur at the center point. So we assume that at this point, the r here is equal to 0, and the u will become u maximum. So that's why we use the idea of u max occur at r equal to 0. So and then if we substitute here, we could get the value of c is equal 3.6 times 10 by the power of 5 Newton meter square second square. Okay, so this is quite just a simple calculation, but in chapter 1 tutorial is actually one to give you an idea about the fluid flow. Okay, so and then for this one is to calculate the wall shear stress actually. So and then what we do is, okay, we know the equation of u. Okay, here we have the common, okay, here this is the equation for the common u, means the equation that could give a pattern of the velocity increment. So we calculate by substituting the coordinates or by substituting the boundary condition, we could find the value of constant here, which is this one. So and then the second question is asking us about the wall shear stress. Okay, here we need to refer with the idea of tau is equal mu du dy. Okay, so this is the idea. And then if you refer, again, because previously I give you an idea of, we have the Cartesian coordinate and we have the polar coordinate. Okay, so normally in Cartesian coordinate, we will use tau is equal mu du dy. Okay, so because the idea is we are focusing on the moving plate like this. So let's say we have a fixed plate at the bottom, and then we have a moving plate at the top here. So by having this one, so we assume that du dy means the difference of velocity between the maximum and the minimum one, the top and the bottom plate, and y will show the gap here. So but now we are discussing about our application is in circular pipe. So in circular pipe, so we change a little bit the equation become this one. So we have tau is equal mu du dr, because we have a circular pipe here. So the maximum velocity is at the center point, and then the shear stress, okay, is reduced when the value of r is become larger and larger. So it is actually in Cartesian coordinate, it is equal to du dy. Okay, so and then we have this one, and then in Cartesian coordinate again, I think you already know that we put a condition. So tau is equal mu du dy. So we put at equal y equal to 0. Why we equal to 0? Because we have a fixed and moving plate like this. So, and then this is moved at certain velocity. So we assume that at y equal to 0 here. So here the y equal to y1. Okay, so at y equal to here 0 here, the shear stress is the highest one. Okay, so and then, but in circular pipe, we cannot put the limit of r equal to 0. Yes, we are using du dr, but we cannot put r is equal to 0. Why? Because in circular pipe, when r equal to 0, so it is the shear stress is the minimum, or the shear stress might be disappear at that moment. So we need to write r equal to capital R, showing that the maximum shear stress occur at the surface of pipe. So at this location, the r is the maximum radius. So we put the r equal to r, and then we get the value of shear stress here is 3,600. And again, just to show you, sometimes we need to we calculate Renault number just to show the condition of its velocity. So this is nothing not about the question. Okay, what I want you to know here is, okay, after this, we will solve problem by using the Navier-Stokes equation and so on and so forth. I hope you could understand what is the meaning of du dy, du dr, and so on and so forth. Okay, might be this is just a mathematical, means it show might be the gradient. So, okay, so it is the difference of velocity in terms of y-axis and so on and so forth. But sometimes you could interpret this one into the changes, mean the delta u over the delta y. That's why it comes out u is 2u2 minus u1, y become u2 minus y1, because we interpret as the difference in y-axis and the difference in terms of velocity. So means that not just understand, not just remember that equation and substitute with any value that you have. You need to understand what it's mean and what your application, what condition that that equation will reflect. Then you solve that conditions by looking at your applications. Okay, because after this you will conduct your master project and so on and so forth. If you do your master project in fluid mechanics, so this is quite a very important one, because normally we try to solve a little bit complicated in machine and so on and so forth, but that diagram is not show in any textbook, because in any textbook they will give you a very basic situation. Okay, you need to interpret by yourself, so what is equal to what and so on and so forth. Okay, so this is the idea of velocity distribution. So this is just a question from the books. So it is show that at application of the rotating cylinder. So as we know that the rotating cylinder is occur when we put some element that's called vortex. Okay, so when it's called vortex here, so might be in this question. So it's we need to calculate the vorticity and strain rate in each part of the flow. So and then here is the limit. Okay, we just follow the question. Okay, so this is the vorticity. As you know, the vorticity, we learned about this in our previous notes. So we have the first to get the to make sure that you will have the cylinder is we merge the linear plus the doublet. Okay, and then you will get the cylinder and the linear flow like this. Okay, so and then this is the stagnation point. So and then if you plus the vortex here, so the vortex will rotate this cylinder at certain velocity, and the vorticity here is actually the circulation. So you have the vorticity here is about the gamma, the circulation divided by the area of the circulation. So we have the vorticity. In the simple words, vorticity is telling you about the tendency of something to rotate. Okay. So here is to simplify, just simplify the question. At the beginning, we assume that there are no VR and there are no VZ. Why? Because you need to understand that this is the component velocity. So mean if the VR and VZ is occur, so the rotation will become like a tornado like this. Okay, it will become bigger and bigger and bigger, and it's moved at certain direction, because we are just want to focusing on on one molecule here that rotates, that flow in circular motion like this. So we assume that it has vortex. So to make sure that this molecule will flow at the same track every time here, so we need to assume that VR and VZ is equal to 0. If not, the VZ here is showing that if you have a molecule move like this, okay, you have a molecule here. So let's say this is a Z axis, so that the molecule will have the Z axis. At the same time, it will rotate at V theta. So this is a VZ, and at the same time, it will move at outside here VR. That's why the diameter of this path is become bigger and bigger. Okay, you need to understand that you need to imagine that sometimes when you want to solve a problem, so please try to eliminate the unnecessary condition. Okay, but sometimes, okay, let's say if you want to make evaluation of a tornado, so means that you need to have this one. Okay, I never do the tornado analysis and so on, but I think might be you can do it part by part. For example, if we just assume that all the velocity here, okay, it's moving at a ring. So means that, okay, you need to calculate every height of this tornado. So and then you could plot the velocity, and then you could calculate the pressure and so on and so forth. Or later on, we'll see not about the tornado, but how to use the Navier-Stokes equation, because the Navier-Stokes equation will have three-dimensional. So you have the x-axis, the y-axis, and the z-axis. So what you know is actually you could plot the pressure of that point in terms of effect of x-axis, y-axis, and z-axis. Okay, so this is just to introduce you about the rotating cylinder. So we have this vorticity. So and then for the question, so let's say for R less than capital R, so we change the value of V naught here with R omega. Okay, this is about the idea of when you have rotational speed. Okay, so you must know that we have a rotational speed and also we have a linear speed. So the rotational speed is something like omega or radian per second or RPM. Okay, RPS, rotation per second. This is rotation per minute. So this is all telling you about the rotational speed. However, linear is something like they give you units about meter per second. But sometimes, okay, sometimes you need to convert the linear velocity and the rotational velocity, and the relationship is U is equal R omega, and it is also equal to pi dn over 60. Okay, so U is meter per second, R is meter, and omega is radian per second, and pi dn is D is diameter, N is RPM. Okay, so and this RPM, we need to divide by 60 here to make sure our unit in second. Our unit is in second. Okay, that's the common relationship that you should know about this. So and then let's say we substitute this one. Okay, because we want to take advantage of this R here, so it can be neglect. And here, okay, so we have and we could neglect the value of R here, and when we have D over dr in bracket of R omega, okay, please try to solve this one with the idea of partial differential. So when you have a partial differential, okay, what you need to do is you need to fix one parameter and you do the differentiate. You need to differentiate with the other parameter. So from here, might be you could fix the R and you have d omega dr, and then you plus with the omega with the R over dr. Okay, so and then you have this one. So previously, so we could have R here and R here. So and then we could neglect dr over dr is equal to 1. And now we have omega and omega, but we have d omega over dr. So and then you need to know that. So the so we says that d omega over dr here is equal to 0. Why? Because we assume that there are no previously, so we are know the value in term of R. Oh, I'm sorry. Okay, that's why it's become omega plus omega. Or, okay, you could just imagine this one because I think it is, okay, I'll take this one. So if you want to have dr, so maybe it's okay if you want to just d over dr, and then you add r omega here, and then you are differentiate with the r here. So the d for dr is 1, so you will get an omega. Okay, so it's both actually will give you the same ideas. Okay, so this is just the substitute with this equation only. Just so you could have. Okay, so for this one, so we just substitute everything. So you will get it is equal to 0 here. So and then this is the another equation to get the value of vorticity. So this is when we use the idea that in our previous note from the Cartesian from the polar coordinates. So we derive the vorticity. We derive the vorticity. Okay. So another thing is in polar coordinate. In polar coordinates there are so many ways to write the velocity. Sometimes they will use u theta, u r, and u z. Okay, sometimes they will use u prime, v prime, and w prime. Okay, so they just want to differentiate just want to use the same terms of Cartesian coordinate. So for Cartesian coordinate, they will use u, v, and w. Okay. So this, okay, for the strain rate. Okay, so this is the equation. So we go very quick this one because this is not our focus actually. Just to have a notes. So at the strain rate, we have this equation. You could have this one. Okay, and then if you substitute, you will get a certain value. So I skip this one. Okay. So and then this one. Okay, for 1.7. Okay, so for 1.7, I need to we take a break around 10. Okay. So this we have a u which is x over 1 over t, and v is y over t. So and then we need to comes out with the stream function equation. So and then we use the Cauchy-Riemann equation. So we have this one. So we have u equal d psi over dy and v equal d psi over dx. So in some textbooks, it will neglect the terms, the negative, because in our syllabus previously, in our undergraduate, in UTM undergraduate level, we take that v is equal to negative d psi over dx. Okay, so this is the okay, let's say. So
counterclockwise.
yes.
Why we should neglect it?
So it's actually I follow the notes inside the books, inside the textbook. Okay, so actually the negative sign here is to show, just to fix the counterclockwise is the negative one.
Yes.
Okay, so if you see the textbook, it neglect the sign. It is okay for you to put the sign.
Okay.
Okay, so because the difference when you have negative or not is, for example, the stream function here, okay, is to show the flow of the fluid. Okay, if you neglect the sign here, maybe you will get the reverse direction. So means that the flow might be flow from the right to the left, and if you get neglect the negative, might be you get the flow is right to the left. But if you have the negative, might be you have the left to the right. So that is the difference. And this is not critical. Why? Because if you do more in stream function research like this, so actually it's depend, you will suit your application in your own coordinates. Okay, for example, if you have a water flow, a river, for example, you have a river here. Okay, and then the water is flow from the left to the right. So it is okay for me to simulate this flow by assuming that the water is flow from the right to the left. Why? Because I will say that, okay, I'm standing at this side. If I standing at this side of the river is flow from my right to my left. But if you are standing here, you will say that the flow is to the left, from the left to the right. Can you get it?
Yes, yes.
Okay, so okay, but in our textbook in viscous fluid flow, they neglect the negative, so I took the negative
Okay.
because I thought you will see the textbook. Okay, it is okay. Okay, so and then we rearrange this equation. So we arrange this equation. So we have u dy, and then we because we could have this one and this one, so we equalize these two equations. So we have uy equal v dx, and then we rearrange again. So we have dy over v is equal dx over u. And what we have here is we have the value of u, and we have the value of x, so we could write as this one. So we have dy over v, so we substitute with the v here. So and then y over 1 over 2t. Okay, so we substitute with the v, and then we substitute with the y, and then we rearrange, okay, by having this one over here. Okay, so we have, okay, so we just solve this one. So we have 1 over 2t over y dy, and we have this one. And then as you know, if we have a 2 dy here, dy on your left and dx on your right, so the way we need to eliminate the differentiate terms is by integrate both of these equations. So we integrate these two equations, we integrate both sides. So we have this one, and then finally we could write the value of y is equal of this one. So and then,
excuse
yes,
me.
yes.
Why we manage the two questions together?
Why we?
Can you please go back to the previous page? Yeah, the last line. Why we manage two question together?
Two equation.
Yeah, it can be simplified as this way, but why?
Okay, you must know that. Okay, the u and the v is the component velocity.
Yes.
Okay, so the component velocity means that you have a one molecule here. So you have a component velocity of u, and you have another component velocity of y, which is v.
Yeah.
Okay, it's actually reflect for one molecule. In real world, so it is actually the movement of the one molecule. So because of these two components, the molecule might be flow at this direction. Okay. Okay, that's why. So, and why we could merge this one. Okay, in previous notes we told you we have lecture about Cauchy-Riemann equation.
Yeah.
Okay, so the Cauchy-Riemann equation is telling us about when we have these two velocity. So and then each velocity will represent the stream function of x, and this is also the stream function of y, and then the combination of these will get us the total stream function, the stream function of combination. Okay.
Okay.
Okay, because we are reflecting in real world, we are reflecting the real one molecule here, and then that's why we could say that we could equal this one, because it is just the combination of these two. The real flow of this molecule is actually the combination of these two component velocity. Okay, so and then we get the value of y, and then again, okay, when you yc. Okay, so again, when you have when you do the integration, okay, you will get constant. So and then if you merge this, you eliminate the term of ln here. Okay, you will get y is equal constant times x by power of this one, and then we need to calculate the value of this constant. So again, the value of this constant can be found when you substitute any point on the line, mean any point at the stream function. So for example, if we substitute the value of y naught, x naught, y naught, so we substitute in the value here, so we'll find that c is equal of this one, and again we substitute the value of c in the common equation, so finally we could get this final equation. So this is actually we will go through back this idea in chapter 2 and chapter 3. Don't worry, because this is just the chapter 1 is actually just to brief you what is the common situation that will occur for the next chapter. Okay,